In section 6.10, we're going to do a quick introduction to hyperbolic functions, but we're mostly going to focus on derivatives and antiderivatives, which are actually the easy part of the section. So when you took trigonometry, you learned about sine and cosine, as well as some other trig functions, and we call those functions circular functions because you can find their values on the unit circle. So if we knew what this angle was, that point where the angle meets the circle would have an x-coordinate and a y-coordinate, and they would also give you cosine and sine of that angle, theta. So we call these circular functions. The equation for this circle is x squared plus y squared equals 1, because it has a radius of 1 and it's centered at the origin. And we've got a bunch of trig identities that look similar to this. If you think of like the Pythagorean identity, says that sine squared theta plus cosine squared theta equals 1, which matches perfectly with x squared plus y squared equals 1. So the difference with hyperbolic functions is that hyperbolic functions satisfy a hyperbola. So the only way that we make a distinction between hyperbolic functions and regular trig functions is this h at the end. So this is hyperbolic sine. You might hear somebody call it sinh, just for short, or cosh. So that's hyperbolic cosine. And the difference with these is that they don't satisfy the equation of the unit circle. They satisfy the equation of a hyperbola. And a hyperbola looks kind of like two sideways parabolas. And the equation for this hyperbola is x squared minus y squared equals 1. And again, any point on this hyperbola, it would have the coordinates x, y, but those coordinates would also be equal to hyperbolic cosine and hyperbolic sine. So it's got a lot in common with our regular trig functions. There's just a little bit of a difference. First of all, in the notation we see with the h and the fact that they satisfy a hyperbola instead of a circle. Those similarities are actually going to make the calculus part of this really easy. Before we get to the calculus part, though, there are some algebraic formulas for hyperbolic sine and hyperbolic cosine. If you've got a graphing calculator, you most likely don't have a hyperbolic sine or cosine button, but if you scroll through the catalog of your calculator, you can find them if you ever needed to calculate a value for any of them. But you also could calculate the value based on their formulas, and hyperbolic sine for any value is the same as e to the x minus e to the negative x all over 2. And then for hyperbolic cosine, it looks exactly the same but with addition. E to the x plus e to the negative x over 2. So there's also a way to calculate these just using exponential functions. The calculus part of this is actually really easy. We've got to remember all of our Calculus 1 rules in terms of product rule, quotient rule, chain rule. We just need to remember the new derivatives for these functions. And we're only going to worry about hyperbolic sine and hyperbolic cosine right now. So the derivative for hyperbolic sine of x is hyperbolic cosine of x. just like it is with our regular sine and cosine. And the derivative for hyperbolic cosine, well, with regular sine and cosine it would be negative, but with the hyperbolic it's not. So the nice thing about calculus with these functions is we don't have to worry about remembering when we have that sign change when we do derivatives and antiderivatives. And we can combine these two new functions with pretty much everything else we've learned in calculus to do some derivatives. For example, if we want the derivative for hyperbolic sine of x squared minus 1. So this is just a chain rule. We've got an outside function and an inside function. So chain rule says first take the derivative of the outside part, which is hyperbolic sine. His derivative is hyperbolic cosine. And you never change what's inside unless you use a trig identity. But then we also have to multiply by the derivative of the inside function, which is 2x. So we would have 2x hyperbolic cosine of x squared minus 1. The derivative for hyperbolic cosine cubed. So I know we've said this before, but you need to think of that exponent of 3 is really applying to the entire hyperbolic cosine value, and possibly even write it out differently just so you can see exactly how the chain rule is going to work. So chain rule says first do the derivative of the outside piece, which is the cubed. So when we do a cubed, the old exponent comes out front, we rewrite the base, and we subtract 1 for the new exponent. And then we also have to multiply by the derivative of our base, which was hyperbolic cosine, and we get hyperbolic sine. And if you want to, you can rewrite it back in the form that it was given to us and avoid some of those parentheses. 3 hyperbolic cosine squared of x times hyperbolic sine of x. Antiderivatives are just as easy. They're just doing these derivatives backwards. So the antiderivative for hyperbolic sine is hyperbolic cosine. Antiderivative for hyperbolic cosine is hyperbolic sine. Again, we don't have to worry about any sign changes, which is nice. Oops. And like most of our more complicated trig antiderivatives, we'll probably, if we're ever asked to do any of these, going to have to do a u substitution. And the u substitution is for that angle. So I'm just going to do one of these really quick, and then we're going to look at a application problem. So if we want the integral of x hyperbolic cosine of negative x squared plus 4. Well, we see a product here of two functions of x, and I also see a composite. So that tells me I'm going to have to do a u substitution. And the parentheses are a dead giveaway for what exactly our u is going to be. U is going to be the negative x squared plus 4. That's going to make our du negative 2x dx. And we have an x dx that we can get rid of, but we don't have that extra negative 2. So I'm going to divide that over and use it as part of my substitution. The x dx can get replaced with negative 1/2 du. And when we rewrite our integral, the x dx is gone because it gets replaced with -1/2 du. We still have the hyperbolic cosine, but now it's just a u inside of it. That -1/2 is just a coefficient. Since it's multiplication, we can just pull it out front and forget about it until the end. And we're really just left with finding the antiderivative for hyperbolic cosine, which is hyperbolic sine. And then we just rewrite in terms of x. So none of our calculus has changed. We just have a few new functions to learn derivatives and antiderivatives for. And you might ask, why in the world do we need to know these? There's actually a lot of real-life shapes that can be modeled with hyperbolic sine and hyperbolic cosine. One of them is the St. Louis arch. If anybody knows, St. Louis arch is this giant arch built in St. Louis, and it's actually, the shape of that is modeled after the hyperbolic cosine function. Also, when you see the bending of wires between electrical poles, they kind of look like a parabola, and in algebra you might have just used a parabola to model that shape, but technically it's a hyperbolic cosine function that makes those shapes. It's a better model to make those shapes. So we're going to look at one quick example. And this is just an example out of our textbook on page 501, example 7. And there's a nice picture that goes along with it. I'll recreate the pieces that we need, but I'm definitely not going to be able to draw it as nice as the book has it. It wants us to find the length of a catenary, and that's what that, when you have a sagging wire or a sagging rope fixed between 2 points, that's what it's called, a catenary. And they've got this really nice picture, and they've put a XY axes on there for us. And there's this cliff on both sides, and a hiker attaches a rope from one side to the other. And there's no way you're going to be able to pull that perfectly tight without some sort of machine helping you. So there's going to be a little bit of sag in it. This gravity's going to pull down any slack. And based on the 2 points that it's fixed at, they're able to come up with the formula for this catenary. And we are asked, bear with me just a second, I'm going to copy this over. A climber anchors a rope at 2 points of equal height, separated by a distance of 100 feet. So what they're telling us here, if we're considering this to be 0, that's our y-axis and our x-axis, they're calling this 50 and this -50. That would give us a total of 100 feet. And the height is the same on both sides. He does this in order to perform a Tyrolean traverse. The rope follows the catenary f of x equals 200 hyperbolic cosine of x divided by 200 over the interval -50 to 50. We want to find the length of the rope between the two anchors. So this is going back a few sections for where we were finding arc length along following a function. So we've got our limits of integration. Remember that formula for arc length is the integral from a to b of the square root of 1 plus f prime of x squared dx. So we've got our function, we've got our a and our b. We need to figure out what f prime squared is. F of x is 200 hyperbolic cosine of x over 200. So for f prime, 200 is just a coefficient, so it gets carried along. The antiderivative for hyperbolic cosine is hyperbolic sine of this same angle. But then we also need to multiply by the derivative of that angle, which is 1 over 200. And very conveniently, that 1 over 200 will cancel out with the 200 we have in the front. So we get f prime of x equals just hyperbolic sine of x over 200. So when we plug that into our formula, we're going to have to square it. There. So our arc length is going to go from -50 to 50, square root of 1 plus hyperbolic sine squared x over 200 dx. On page 493 of our textbook, you will see some identities for hyperbolic trig functions. They're fairly similar to what we use with our circular trig functions. Some of them are just slightly different. But the one that we're going to be interested in to make this problem a little bit simpler says that hyperbolic cosine squared minus hyperbolic sine squared equals 1. And we can just rearrange the terms in that identity, and we will see that our entire radicand can be replaced with hyperbolic cosine squared. So I'm going to add that hyperbolic sine squared over. And we've got the exact same thing. The angle doesn't matter as long as we keep the same angle when we do the identity replacement. So that entire radicand can be replaced with hyperbolic cosine of x over 200 squared. And now that we've got it simplified down to just a single term, we can cancel the square and the square root. And now we're down to something much more manageable. All we have to integrate is hyperbolic cosine of x over 200. So I'm going to do a quick little u substitution for my angle there. If we let x or u equal x over 200, then du is 1 over 200 dx. But there's no other 200 in this problem to get rid of, so I'm just going to multiply that over. And we get that dx can be replaced with 200 du. And that gives us 200 hyperbolic cosine of u du. So now the 200 is just a coefficient. The antiderivative for hyperbolic cosine is hyperbolic sine. And we're going to rewrite this back in terms of x so that we can evaluate. So remember, u was x over 200. So we'll plug the 50 in first. 50 divided by 200 is just a quarter. So we've got 200 hyperbolic sine of 1/4 minus, we plug negative 50 in, we get negative 1/4. So 200 hyperbolic sine of negative 1/4. Now if you want to look at those identities, we could probably simplify this down even further. We also could just go to our calculator and figure out what these are. If you can't find hyperbolic sine on your graphing calculator, you can look through the catalog and find it. Remember, we also have that option to changing it into exponential form. So if you really wanted to do this by hand as much as possible, we would write this as 200 e to the 1/4 minus e to the negative 1/4 all over 2 minus 200 e to the negative 1/4 minus e to the positive 1/4, because when we negate that, it's back to positive, all over 2. We want to see a lot of stuff that's going to cancel here. So 200 divided by 2 is 100, and we can distribute it. And if we distribute here and divide, we get minus 100 e to the negative 1/4 plus 100 e to the 1/4. So I have a total of 200 e to the 1/4 and then minus 200 e to the negative 1/4. Now, those do not cancel out. They've got completely different exponents, and if you look in your calculator, e to the 1/4 and e to the negative 1/4 are not opposite values. They're two completely different values. But now it's much more manageable at this point, especially if you don't have a graphing calculator. We could easily type that in from our home screen. And when I do, I get about 101. There's a little bit of a decimal there, but it's really not much. And our units here were feet. So this rope is pretty tight. If you look back at the graph, that entire distance, straight line distance between them was 100, but the total length of rope we need is only 101. So we only need 1 extra foot of rope, which means it's not sagging that much. It's pretty taut. So it's a lot of new formulas. You do not need to memorize them. The only thing I want you to know, possibly for the test, are what the derivatives and antiderivatives for hyperbolic sine and hyperbolic cosine are. So I'm going to star these. You don't need to know any of those identities. If there's anything like this on the test, they'll be pretty straightforward, just derivative, antiderivative problems.